Section 7.4. All right, so now we get to actually start doing hypothesis tests. We're going to go from start to finish. I spent the last several videos kind of pontificating just about how we think about hypothesis tests, what it all means. Now we get down to the meat of it. We get to actually do it. All right, so as we do it, before we do this, let me just kind of give you a brief rundown. And by the way, we're going to have two different types of hypothesis tests. In 7.4, we're going to focus on those that use the normal statistic. And then in 7.5, we'll focus on those that use the t-statistic. So we'll look at each of those one at a time. But first, let me just kind of review the types of things we're going to do. So the first thing we're going to do in every hypothesis test problem is we're always going to write down our hypotheses. And for our problems in this section, our hypotheses H0 will always be that mu is equal to, and then you choose a number. Now, again, choose a number, do not write a hashtag, write down whatever number that is, okay? And for our alternative hypothesis, it'll always be either mu is greater than, mu is less than, or mu is not equal to that same number. So those numbers are going to be the same in both of these problems, okay? So, and then only choose one. Choose whether it's greater than, less than, or not equal to, depending on whether it's appropriate. Now, for this section, our test statistic is always going to be z is equal to x bar minus mu divided by sigma over the square root of n. Now, let's ask, let's just go through what do these letters mean. Z is the number we're calculating, so z is the statistic we're going to use for the rest of the problem. X bar is our sample average, so this is the average from whatever our individuals were in our study. So you did some sort of experiment, you came up with an average, that average goes right here. This mu is the average that comes from your hypothesis, so this mu and this will always be the same number as well. So whatever you're starting with your null hypothesis, that will be your mu that shows up down here. Finally, your sigma is your standard deviation, and that's the standard deviation for the whole population. So this is the standard deviation that you know is true for the whole population, and n is how many people are present for your study. So there's a good question that's always worth asking, and the question is when to use this. And there are two possibilities. One is when you know what sigma is. So if you know the standard deviation for the whole population, then this is the formula you're going to use. So if for some reason people have studied this problem enough, like for example, if you're doing a standardized test like the SAT or ACT or an AP exam, those tests have been done so many times that we know what the standard deviation is for them. So if you happen to know the standard deviation before you start the problem, then this is the formula we're going to use. The other option is if n is really big. So if n is really big, then it works fine, because then whatever our standard deviation is pretty close to the standard deviation for the population. So how big is really big? Usually people take 30 as kind of the standard point where it needs to be big enough. I would probably actually go even further and want to make it even larger than that, like somewhere closer to 100. But 30 is usually kind of the statistics point where people start going from this formula to the one we're going to go into the next section. So if it's big enough, then the difference between the standard deviation from your sample and the standard deviation from the population is so small that you can put your standard deviation here for sigma and keep going. Okay, so there's our hypotheses, there's our test statistic. Now once we've calculated our test statistic, let's just do like a scrolling thing here. Now once we've done our test statistic, we're ready to find our p-value, and we know from last time that our p-value is found by putting whatever that test statistic is on here and finding the correct side. So I put the right side because this is a picture of a right-tailed test, but we know we could also have left or two-tailed. It really just depends upon the problem that we're dealing with. And what do we do to find this p-value? We use a normal distribution, and we use mu equal to 0 and sigma equal to 1. So that's what we want for this p-value. Finally, our conclusion, we have one of two options. Either Our P is less than our alpha. What was alpha from last time? Alpha was that level that we decided if it's below this, it's small enough. So if P is smaller than that alpha value, we reject the null hypothesis. And if P is greater than that alpha value, we fail to reject our null hypothesis. So we either reject our null hypothesis or fail to reject a null hypothesis. Okay, so this is our overview of our test. So let's get ready and let's do our problem and see how it goes. So we're ready for problem 7.4. All right, you know that when the speed limit is 65 miles per hour, the speed of drivers in Texas is normally distributed with mu equal to 67 and sigma equal to 4. You're curious if the drivers on the loop are significantly different from those throughout the rest of the state. You do a study on the average speed of cars driving the loop on a Friday evening. You measure the speed of 50 cars and find that X bar is 6.75. So first, we need to come up with our hypotheses. So this is a great point for you all to stop, see if you can write these hypotheses correctly. So pause it here, see if you can get that. All right. Well, what we need to say is if there's nothing different between our drivers on the loop and drivers everywhere else. So if our drivers on the loop are same as every other driver in the state of Texas, then their average is going to be 67 because that's the speed for all drivers in Texas. Meanwhile, we're curious whether the drivers are different from the rest of the state. So notice that second sentence. You're curious if the drivers on the loop are significantly different from those throughout the rest of the state. Notice we didn't say, are the drivers in the loop greater than the rest? We didn't say, do drivers in the loop go faster or slower? We just said different. So I'm just going to put not equal to 67 for my second one. What does that tell me about my problem? Well, you can see that my answer to part B is that this is going to be a two-tailed test. A two-tailed test because we're using this not equal to sign here. And we can also see from part C that we're going to use a normal distribution. Why is it a normal distribution? Well, we are told that sigma equals 4. So we're told what that standard deviation is for all the drivers in the whole state. So since that's a known number, we're going to use a normal distribution. So what do I mean by normal distribution? We're going to use our Z formula. Okay. Well, let's come over and it's time for us to start calculating our test statistic. So what is our test statistic? Our test statistic is from last time, from earlier, Z equals X bar minus mu divided by sigma over the square root of n. And now it's a reading problem. Can we read the right things to fit in? That sounds easy, but actually it can be quite a challenge. So often the hardest part is looking through the paragraph of words and sorting out what is what in this paragraph. Well, X bar is the average. The X bar is the average from the cars that we studied. And so our X bar was 65.75 because for our 50 cars, that was our average. Mu is the number that came from our null hypothesis. Mu is 67. Sigma is 4 because that, again, came from our problem. And then N is how many cars we studied. And you'll notice that it says we studied 50 cars. All right, so now we're going to want to plug all of this into our calculator and come up with a number. This can actually be quite tricky, so be careful. So a few things that I see, let me just write a few things that I see people do on their calculators that are going to give them wrong answers. So I see students just writing something like this, 65.75 divided by 67, or minus 67 divided by 4 divided by the square root of 50. And what's this going to do wrong? Well, your calculator automatically does the order of operations. So your calculator is going to divide this first and then divide this second and then subtract from your answer. notice we want to do the subtraction first. So we need to make sure that we are calculating these together. So if you have a calculator with parentheses, you can put them in parentheses. If not, you can just hit subtract and write whatever that number is down there. But even if you type this, you'll still get the wrong answer, because this is going to take this answer and divide it by 4, and then take that answer and divide that answer by 50. So this calculation here is 65.75 minus 67 divided by 4, and then dividing all of that by the square root of 50. Well, this is a different mathematical problem than the one we started with. So this is not what we want. So we also need to do the 4 and the 50 together first. So what I might suggest is that you just grab your calculator and do these two subtractions. And so do 65.75 minus 67. I should be able to do this in my head, but oh well. And I get a negative 1.25. And then maybe just do the bottom in your calculator also. And then do 4 divided by the square root of 50. And that's going to give me 0.565. And now I can divide those two things. Now, if, however, you're really good at typing in a whole bunch of stuff in your calculator, go for it. I'm happy with that. But if you find that you're consistently getting the wrong answers, or you're not getting this 2.21 number or something similar to it, then I would recommend that you just do each piece and write the piece down, and then write your answer down. Okay, so here we go. So this is our test statistics. So for part C, part D, this is the answer we're looking for. Now finally, let's try to find our p-value. So notice we have a two-tailed test. So that means I'm going to have this kind of picture. Negative is going to be on this side, negative 2.21, and positive 2.21 is going to be this side. And because it's two-tailed, I want to highlight both sides. And so there's going to be two ways that we can go about doing this. Let's grab our app and calculate. So we are on our normal distribution still. We've got 0 and 1. And so we're just going to put negative 2.21 in here and hit enter. And you'll see right now I have it set up like a right tail test. If I use this one, it's going to give me a two-tailed test, and now I can see that it has my picture. Now I can see it has my picture looking just the way I want it. It has both the left side and the right side showing up, and it looks like my answer is 0.027. So P is 0.027 right here. Now, what could I have done if I was on my computer, or if I was on a calculator? What you could do is you could do this one, and notice that picture is going to give me just one of the tails. I could have done 0.016 or 0.135, and then multiplied that by 2, and that would have given me 0.027. So you could have just done one of the two sides and then multiplied that side by 2. Okay. But at any rate, our p-value is 0.027. And now once we have that p-value, we're ready to come and draw a conclusion. And this is where I have the notes for the level of significance. I talked about that in the last section, so make sure that you paid attention in 7.3, and this makes sense. But really, we have two options. Option 1, if alpha is equal to 0.1, then what do I notice about my p-value? The question is this a really small number? Well, here, if I use 0.1 for my alpha, then 0.027 is smaller than 0.1. So my p is less than my alpha value. What does that mean for my conclusion? So my conclusion here is that we reject H naught. So let's think a little bit about the logic here. We started with this assumption. That the mean was equal to 67. We've done all this work. We found the probability of picking 50 cars and having the speed that we had, or something more excessive, is 0.027. So 2.7%. Well, if I want my alpha value to be 0.1, that is if I say anything less than 10%, I'm going to say is a small enough number, then this number is small enough. I go, well, this is an unusual result, and so therefore I'm going to reject H naught. So the only conclusion I could make is that this assumption that the mean was equal to 67 is actually wrong. So I'm going to reject H naught, so that means the cars do travel a different speed on the loop. Uh-oh, I'm out of space here. On the loop. Okay, so that's what we did if alpha is equal to 0.1. But now, what if I were to change my alpha value, and I made my alpha value 0.01 instead? Well, now, if my alpha value is 0.01, I'm going to get a different set of results, because now my 0.027 is actually bigger than 0.01. So now I fail to reject. So now I fail to reject H naught, because this time P is bigger than my alpha value. So it all depends on what you choose for this number. Again, you won't have to choose it. It'll be told to you from me or from the textbook. But whatever you choose for this number, you have to determine, am I bigger or smaller than my number? If I'm smaller, then I reject. If I'm bigger, then I fail to reject. What happens? What does it mean if I fail to reject? That means not enough evidence to conclude loop is different. Okay, I'm parsing my words because I'm running out of whiteboard space. But what you can see here, right, is that you have one of two possibilities. Either it's smaller, and if it's smaller, then you can say, oh, our cars on our loop are different. We're able to reject our null hypothesis, and we're able to make a conclusion. If it's bigger, we don't make a conclusion. Instead, we say we don't have evidence to make a conclusion, and that's all we come to. All right. Well, I hope this makes a little bit of sense. Look at those problems. Again, you'll have to flip over a page to see the 7.4 assignment. It's on page 43 in your notes. Try the problems. Hopefully they make a lot of sense. And then come back and watch the video on 7.5, and we'll learn how to do tests when we don't know what sigma is. Spoiler, it's pretty similar.